Hello everyone, welcome to my presentation about geostrophic balance. We're going to start by defining what geostrophic balance is. Geostrophic balance is a balance of forces where the Coriolis force is balanced by the pressure gradient force. And in this presentation we're going to talk about what those two things are. It is also what leads to steady ocean circulation in the ocean, and as shown in this diagram, it is the reason that we get steady wind flows in the atmosphere. And it is specifically this part of the diagram that shows geostrophic balance, because the Coriolis force and pressure gradient force are equal but opposite forces here, which results in steady wind flow. Right, so we're going to start by talking about the pressure gradient force, which is simply the force that drives the motion of particles from regions of high pressure to regions of low pressure. And that's demonstrated in this diagram. So this is high pressure and that's low pressure, and the force is going against the direction of the pressure gradient. And causes of the pressure gradient force in the ocean are differences in mean sea surface height and density differences. So that's, for example, due to differences in temperature or salinity in the ocean, within the ocean. Now on to the other part, or the other component of geostrophic balance, which is the Coriolis acceleration. The Coriolis acceleration is technically not a force. It's often referred to as an inertial force, or a fictitious force, and it comes about due to the rotation of the Earth. More specifically, it is something that arises because we are considering two different reference frames. On the one hand, we have the rotating non-inertial reference frame of the Earth, because it's rotating, obviously, and on the other hand, we have a fixed inertial reference frame. And we are going to use the analogy of a ball that is being kicked towards a goal to illustrate how this force causes deflection in the rotating inertial frame. So this is the non-rotating fixed frame, and as you can see, a ball that is traveling vertically upwards misses its target, and this is analogous to what's happening to an air parcel in the Earth, or in the Earth system, because at the equator, a point on the equator will move further in the same amount of time than a point at higher latitudes, because all points have the same angular velocity, but the distance travelled by a point on the equator is further, so it's faster. So now if we consider the same situation but in a rotating reference frame, so we're moving with the trains this time, we see how it looks like the ball is being deflected. This is why we call the Coriolis force a force, even though it's not technically a force, because in an inertial frame, so in a fixed frame, we are used to things only changing direction when acted upon by a force. And this leads us to get a new expression for the force acting on an object. So instead of using F equals ma, which is what we normally use, we have to add in the Coriolis force for a rotating reference frame. So this term gives the acceleration within the rotating frame, and this term gives the Coriolis force. And this, as you might notice, this changes the conditions for steady motion. So in an inertial reference frame, the force acting on a body has to be equal to 0, and in a rotating reference frame, the force acting on a body has to be equal to the Coriolis force in order for steady motion to occur. Right, and that leads us all the way onto geostrophic flow and the equations that describe geostrophic flow. These follow the same structure of C equals F. So the pressure gradient force is equal to the Coriolis force, and as I've mentioned before, and this is the condition for geostrophic balance, so this is the condition that needs to be met in order for motion to be steady within the Earth system. Right, I hope that was helpful. Thank you very much for listening.